facilitate this type of reaction. So in culture cell, let's say you take some culture cells and treat with formaldehyde, and before and after you scan the amount of hypoxanthine, you will see that there is an increase. Does it make sense? So those are all nasty stuff, and one has to be careful. Now, nitrous acid, chemical mutagen nitrous acid, converts cytosine to uracil. Again, oxidative deamination. If this is cytosine, can you see? No? Is it better now? Yes? So, we already discussed that any oxidizing agent, oxidative stress will convert adenine to hypoxanthine, so AT to GC, and cytosine, that's the amine group, which also can be oxidatively deaminated by oxidative stress like nitrous acid. Correct? And that would lead to conversion of cytosine to uracil. Now you have a GC-CG pair to AT pair transition. Correct? So nitrous acid can induce AT to GC transition, also via deamination of adenine. Correct? Nitrous acid also can cause GC, CG to AT type of transition by working on cytosine deamination. So all these things are possible. Many alkylating agents, nitrogen mustards, which are used in chemical warfare, Second World War II. Now also we use a lot of type of nitrogen mustards, not really nitrogen mustards, but the pesticides, correct? To treat the gardens and insects, correct? So those are nothing other than reactive phosphates or sulfates. So basically, any reactive molecule like phosphonates, if you have a strong reactive group, the amine will react, and these are some of the examples of pesticides. Highly reactive phosphates, orthophosphates, and so on and so on. Sulfates, so that they can cross-link or block the active site. Okay. So many of these easily react also with the DNA, and they can increase the mutation. Many anti-cancer drugs, nothing other than alkylating agent, dimethyl sulfate, dimethyl correct? I did a wrong drawing. That's dimethyl sulfate. These are highly reactive molecules. If you treat with amine, DNA, okay, they can easily react with the methyl group. If you take the cell, cultured cells, treat with dimethyl sulfate, they will easily react with DNA and get methylated DNA. Methylation is a damage to DNA, and eventually it will have problem. Does it make sense? So many of these reactive molecules in the environment cause these mutations. Alkylation of G residues. Let's see what we have. Alkylation of guanine. Alkylation of guanine, etc. Eventually, so what I am trying to say that many of these highly reactive molecules, alkylating agents, drugs, pesticides, all exposure can lead to increased mutation. Some of them could be repaired, some of them are not repaired. So if you are exposed to certain chemicals and drugs, there is increased risk of cancer. In fact, certain areas or certain counties in the country are at higher risk of cancer than others. What it means that that particular area is contaminated with some kind of toxic chemicals, correct, which are inducing the DNA damage. I think I mentioned to you that many years ago I was involved in a thesis committee of a graduate student from EPA, right? And this girl, this lady was looking at the proximity of the airport to the risk of cancer. Think about that. It's very important, correct? We always like to live close to the airport because you just park the car and go, correct? And that's why actually DFW area is getting highly populated because the airport is so easily accessible. House prices are relatively cheaper, not anymore compared to California and New York, correct? A lot of people are moving, huge traffic over last 10 years or 15 years. But this study actually clearly shows the closer we live to the airport, there is an increased risk of variety of cancer. And that's because one of the problems is air pollution, right? So if you actually stand near the DFW airport, little bit 3 miles away, there's a series of planes are lining up to land. Oh, wow. It's nice to see that, wow, beautiful. But it actually contaminating the air, so we are inhaling every day. Many of these things are nasty, people do not care, but it's time that we care. I'll tell you one story. I think I wanted to tell a story last week, correct? Yes. I was grown up in a rural place. So until my 10th plus 2, I did not have electricity, correct? So we did not have electricity. So I used to light some kind of hazard and study. But those are the beautiful days because night time I used to go, we see the sky full of stars. Now we don't see that, correct? Because so much of light everywhere, you don't see that stars are there. But if you like to see the stars, go maybe a couple of hours drive towards the El Paso and camp some. It's beautiful if you like to do that. The night time, there's a night, it's very different, correct? Those days, population was less, so whatever the rice, wheat, crops used to be grown, that's good enough. But with time, population has significantly gone high, and to supply the demand, we have all these transgenic hybrid crops, correct? Those days, in my very childhood, I used to see the area I come from is Calcutta, and we have huge monsoon. I mean, sometimes it is raining, means it's not raining, it's just pouring, correct? 3-4 days it's water is pouring, and all of a sudden the level of water is above your head in some hill. And we used to grow some rice, and these rice plants, because they have to fight with this large amount of water in 2-3 days, they used to also grow very tall. Some of the rice plants used to be twice as tall as me. Right? So they really, and but only problem with that particular crop is that we could grow only once a year. An amount of rice we used to get is not as much. That's good enough for a family those days. But now people want to make a lot of money, and we don't cultivate that particular rice anymore. We are supplied by the government with the hybrid crops, transgenic crops. But the rice plants are this big, like here, wheat plants, correct? But we have 10-fold more rice. Where we used to get 100-pound rice, now we get 1,000-pound rice. Correct? So we have grown a lot of the pesticide, crops, hybrid crops, and which cannot be eaten by the bugs. They are genetically engineered, correct? Now, one of the problems, people are happy, wow, we are growing so much. People are not hungry anymore, making some money, exporting, importing, correct? Selling all this stuff. One of the major problems what they did, they put a lot of pesticides to block the bugs, lot of fertilizers to let them grow. Correct? Eventually, you have to get the fertilizer from somewhere. If you are growing 3 times a year or 4 times a year crop, you don't have enough fertilizer coming in to the soil. So we are putting a lot of fertilizer. It's killing all the microbes and putting a lot of pesticides, killing everything. Correct? Now, what happens? The interesting part. I was about to go to the college those days, finishing the school and going college, and I see in the monsoon time you have a lot of fish, frogs, because a lot of water. Correct? You grow for 3-4 months, tons of fish. I used to catch a lot of fish. I have seen the cobra fighting with mongoose. That's the area I come from. Correct? We have Sundarban, which is the place of Royal Bengal tiger. Royal Bengal tiger is not only place of Royal Bengal tiger, it is place for deadly crocodiles, deadly snakes like cobra. So it's all deadly. I am not that deadly. Okay? So, because those are abundant, because lots of tropical, correct? Now, because of the so much pesticides, fertilizers, all the frogs are gone, all the fish is gone, so snakes, everybody who are dependent on them, they are slowly disappearing. 80% to 90% of the wild type fish which used to grow wild, they are all gone. What happened? That when this large amount of water in the winter time concentrates, they concentrate in small lakes or ponds, correct? Problem is that so high concentration of some of these pesticides and fertilizer in the water, the fish and frogs cannot survive. I have seen this big fish just standing on the surface of the water. They don't move. Okay? They have so much of chemicals and they cannot breathe, and eventually they will have wounds and they will die. I used to think those days maybe some infection. Those are not infection. Those are highly concentrated poison in the water. So this water people have used over time because that's the source of the water for drinking, and so we have contaminated the really good high quality water into pesticide drink. And now we see every family somebody has cancer. Thyroid, mammary, all kinds of different. So rate of cancer has rapidly gone high over last 20-30 years. We are feeding ourselves with lot of crops and pesticides and fertilizers, but those are part of the gift because we are manipulated. Does it make sense? So now if I go, I have to find really hard to look for some wild type fish, sometimes snakes. They are all disappearing. So many of these chemical pesticides, fertilizers, which we use is not right. Here we actually, these days, we don't find organic fruits and vegetables, correct? Whatever we get with the transgenic. The apple do not get rotten, tomato do not get rotten, correct? You can keep it for 1 month, still they are fine. So these are all transgenic and all kinds of stuff. So we are inhaling, and that's contributing to the increased risk of health. I give you, should I tell another story?
Yes.
Because we are going slow, right? Atrazine. There is a chemical, you should know. A chemical called atrazine. Anybody knows the story of atrazine? See, we need to know. Atrazine is a very common weed killer. So whenever in the lawn or garden where somebody whom you don't want, you just buy this weed killer and spray. Well, plant dies, we are happy. Wow, lawn is so beautiful, green, and so on. I don't put in my garden. There are some weeds and they're part of my life. Correct? So this atrazine people like because it kills very nicely weeds. And I think already maybe 8-10 years ago, a biologist, I think Tyson, Michael, University of California, if I'm not wrong, they are concerned about the endocrine disrupting activity of this molecule. So they took a big pond. Of course, you need the approval from the city and the whatever. So took the pond and put this atrazine powder. Okay, and then he put some frogs. And about 6 months later, he caught some of these frogs and dissected and see if there is anything wrong. And it was really shocking that some of the male frogs are producing eggs. Okay, think about this. It's a huge disaster because these are endocrine disrupting chemicals. They misguide the endocrine signaling, hormone signaling, eventually causes the developmental problem. That's the story of atrazine. Correct? We use DDT. What is DDT used for? Mosquito. Correct? Killing mosquito. So we have pictures that aeroplane, because there are a lot of jungles and forests, aeroplane is spraying large amount of DDT over the big area, mosquitoes are dying. Correct? Disease are not getting. Now we know that DDT is a strong endocrine disrupting chemical. Now here in US it is not used as much, but it is widely used in all other tropical countries, including India, Bangladesh, China. Because we have this malaria, dengue, West Nile, all kinds of viral, correct? Deadly virus is coming and they are carried by the mosquitoes. And whenever there is outburst, correct, of certain form of the disease, still government puts all of these large concentration of disease. But eventually these are coming back to us. Right? Those are nasty. In fact, when you travel, international travel, which I do very often, I travel to India, right? If you go to the international office, international health center, they they will advise you that if you are going to Kenya, what are the vaccines you need to take? If you are going to Calcutta, what are the vaccines you need to take? Because, correct? So when I am traveling to Calcutta, they will give possibly at least 20 different injections. I said, okay, let me die. Correct? I just took one or two typhoid. Still I am alive. So sometimes if you're traveling new, it is really scary. They will think as soon as you touch the ground, you are going to get malaria, typhoid, dengue, West Nile, everything. So these are not true, but it is true that there are some. Okay, one has to be careful drinking water and taking care. Anyway, I think I am giving you a lot of stories, but I think some of these stories hopefully will stay with us for long. Right? So where are we? So these nasty chemicals have a nasty impact on our life. I think that's part of the immunology sections we are not covering in this class, although important. And that's the end of this section on mutation. Anybody has any question? No? Okay. So let's go to the next topic, which is transcription. And regulation of gene expression. And that's my area of expertise in research. But we are not going there in that detail. We will talk about the basics. Okay, so the basic concept you need to clarify and make yourself clear what it means. And I emphasize that you understand the basics, correct? That's how I like. So you have double helical DNA. When it is duplicated, it is replication. When it is transcribed into RNA, one of the strands of the double helical DNA is transcribed to messenger RNA. Messenger RNA is eventually translated into protein. This is common flow of genetic information in your DNA that becomes RNA and protein. And in this, unlike replication in the transcription, the process of copying DNA to RNA is called a transcription. Of course, you need a polymerase. In this case, the RNA polymerase. Does it make sense? Now, there are two strands of the DNA, and only one strand of the DNA is transcribed into RNA. So, transcription, whole DNA is not transcribed. Only the coding sequence, protein coding genes are transcribed, and into this part is transcribed into messenger RNA. So this is a gene. What is a gene? What is a gene? Sequence that codes for a protein. Correct? How many genes we have in human? About 20,000 protein coding genes, and that's about less than 1.5% of the whole genome. Very tiny fraction of our genome actually codes for protein, but that is good enough to make human a human, correct? Dog is a dog. So these genes are nothing other than a DNA sequence which are coded for protein, and in transcription this gene is transcribed into messenger RNA, correct? And this process is catalyzed by RNA polymerase, correct? And this RNA is converted into protein by process called translation. We'll talk in the next chapter. We'll talk about translation, how RNA is coded, translated into protein. So gene normally is expression is regulated by the surrounding sequences. This is called start site, transcription start site, and this particular region which control the expression, transcription of the gene is called promoters. Okay. Now, wherever the transcription starts, this particular site is called denoted as +1, and anything this direction, this is 5 prime, this is 3 prime, this side is called downstream sequences. Downstream sequences, and anything towards 5 prime, this direction is called upstream sequences. Alright? This is +1, first nucleotide, second nucleotide will be +2, +3, maybe +100. It doesn't matter, maybe +3000. Does it make sense? Now, there is a termination site which is called stop signal. Okay? So, gene is a sequence of the DNA which is present inside the DNA, and it codes for an mRNA, correct? For protein coding, which codes for a protein. And this gene is regulated by upstream sequences which are located close to the gene. This is called promoter. And now, +1, +2, these are called downstream sequences. If you go in this direction, these are called -1, -2, -3. These sequences are called upstream. Every gene in our body must be regulated, correct? Otherwise, it will keep on making protein. So whenever we need a, let's say, glycolysis, a TCA cycle to turn on, we want to make those proteins, those enzymes at that time. Whenever there is no need, just shut it down. Does it make sense? There is a strong regulation of each gene which we have. We have like 20,000, approximately 20,000 genes. Not all genes are expressed all the time. Okay? So when the cells are fertilized, sperm and egg, when they are fertilized, you produce a zygote, single cell. It becomes 2 cells, 4 cells, 8 cells, and so on. Now think about it. Single cell is going to give you a completely grown organism. Right? These cells are stem cells. They have ability to differentiate into different cells. If you isolate each cell from here, each cell has a potential to develop a fully grown organism. Those are stem cells. Now, these stem cells, this early stage of development is controlled by certain genes. Okay? Those are early stage of embryonic development, and those genes remain turned off maybe rest of the life. Does it make sense? So out of 20,000, maybe 1000 genes are active here, rest of the genes are turned off. At a different stage of development, new genes are turned on, some genes are turned off. So there is actually very strong regulation of the gene expression throughout the development. Whatever the genes expressed in somatic cells, they are very different whatever the genes expressed in germline cells. Does it make sense? Or muscle cell versus myocytes, cardiomyocytes. So different genes are expressed. Different genes are expressed means what? Basically, the genes are differentially regulated. A gene here is differentially regulated, and this regulation is controlled by the promoter. Promoter is nothing other than the sequence which is located upstream of the gene normally. Upstream of the gene, variety of transcription factors, including RNA polymerase, comes and bind and controls the expression of the gene. Does it make sense? So gene regulation is one of the major, correct, regulation because that controls the cell cycle progression, cell differentiation, development, and misregulation will cause the disease, including cancer. So we need to understand how the DNA is copied into RNA and how this gene is not only transcription, how the transcription is regulated. I think that's very, very important, right? So most of the studies are done what we talk is in prokaryotes, which is very simple, and they're very complicated in eukaryotes. So RNA. Before we go to the RNA, let's talk a little bit of what are the different types of RNA we have. What are the different types of RNA we have? One is, first one, mRNA, messenger RNA, which acts as template for the protein synthesis, correct? Second one, tRNA, which is also involved. What is the size of mRNA? Size, length. It could be very small to maybe few thousand, maybe 10,000, 50,000. It could be, correct? Maybe 100,000. Different mRNA has different length. These are actually pre-mRNA, not really a mature mRNA. Okay? tRNA, approximately 70 to 95 base pair, very small. Ribosomal RNA, ribosomal RNA, which are called rRNA. How big they are? They are pretty big. Correct? Ribosome is the RNA protein complexes which are involved in translation. We will talk in the next chapter, ribosomal RNA. But they could be very big. We need to make a lot of proteins. So there are many ribosomal RNA sequences in our body, in our chromosome. Normally they are very big and big RNA. Beyond these three well-studied classical RNA, there are a lot of new transcripts people are discovering. Can you give me the example? Before that, let's talk microRNA. Correct? MicroRNA, which are called amine RNA. They are also called meat 26, meat 156. Correct? There are many microRNA. They are also coded into the genome. There are many other non-coding RNA, so this also does not code for protein. This does not code for protein, and only mRNA codes for protein. There are non-coding RNA, many different classes of non-coding RNA, which are called ncRNA. They could be short and long. Long non-coding RNA called valencRNA. My lab actually does a lot of research on gene regulation in human system, lot of non-coding RNA. Okay. We are trying to not only understand the function of non-coding RNA, trying to discover new non-coding RNA associated with different disease. So, variety of non-coding RNA, small nuclear RNA, hnRNA, siRNA. There is something interesting coming up. Last 3-4 years, people are finding there is something called circular RNA, which is called cRNA. Apparently, in our circulating blood, there are many RNA which are single-stranded and circular. Okay? Until 2007, people mostly focused on these three types of RNA. Something started coming out. Starting with 2007, we know that 80% of the genome is functional and they code for the many non-coding RNA which are not translated into protein. Does it make sense? And variety of things are coming up. One of the problems is that because it is coming from 80 to 90% of the genome, they are abundant in the cell. Does it make sense? I may have given you this lecture earlier. Correct? They are abundant in the cells, so sometimes they are a lot more than protein coding mRNA. Correct? So right now there are technologies where you can identify, yes, this particular transcript is high in the cell, but nobody knows what is its function, how big is actually size, what is its function in the cell. So what people are identifying is that you isolate the total RNA from a normal healthy tissue and take the, let's say, give an example of take an example of, let's say, prostate cancer. Correct? There is a well-known biomarker for prostate cancer. Anybody knows the name? There is a gene which is called PSA, prostate cancer specific antigen. It's a protein which is overexpressed in prostate cancer. Okay? And you can detect in the blood. When a person becomes 45 or 50 years old, when they go to the doctor for primary checkup, they take your blood. Few things they check. One is the blood sugar level, fasting blood sugar level. They check the blood pressure, of course. and if you check some of the potential biomarker, one of them is PSA. If for some reason PSA level is high, okay, people think this person is at high risk of prostate cancer. Does it make sense? So normally, depending on how bad the PSA level is, okay, doctor recommends that you should go for surgery, removal of the prostate gland. And of course, we all like to live few hundred years, right? So, because we get scared, go for the prostate surgery and all kinds of stuff. I know several people, the big scientists, they have gone to this prostate surgery. Okay, it's a very important plan. Now, when the surgery is done and they dissect the tissue and so on, they don't have cancer. Alright? So about 40%, most of the cancer, they go for surgery because doctor recommends and we are scared. But they really did not need the surgery because they don't have the disease. 30 to 40% cancer surgery is actually wrong. One of them is prostate. So what it is telling is that there is not a big, whatever the biomarker we have, PSA, it's a good biomarker. Yes, the person who has really cancer, their PSA level is high. But for some reason, people do not have cancer, but the PSA level is high. Correct? It's a false. It's not 100% guaranteed biomarker. Does it make sense? So under those circumstances, the doctor cannot do anything because they don't know what else to do. Most of the oncologists don't know what to do. Right? Don't tell any oncologist they'll come and say, right? Take my job or shoot me, do something. Right? Because they look at the cancer depending on the type of disease, they do the surgery, give the chemo and all kinds of stuff. But they have experience which matters. Correct? So there is no efficient biomarker. So there is a huge need of developing biomarkers which are highly accurate. Does it make sense? Or at least not highly accurate, closely correlated to the disease so that we can save this 30 to 40% unnecessary surgical removal of the gland. Does it make sense? So now, the lot of potential biomarkers are coming based on the non-coding RNA. So control tissue and prostate cancer tissue, you isolate total RNA. Total RNA. Correct? You take the cells from the control of blood sample or tissue sample. There are plenty of procedures. You can isolate the total RNA. Total RNA means it contains all of these. Right? All of these mRNA, tRNA, all kinds of RNA you can actually identify. Correct? Isolate the cell, and then there is some technique called RNA sequencing. It's not exactly sequencing. It's it's called RNA sequencing, but it's not exactly sequencing. It's a high throughput technology. And in this technology, it's a kind of microarray. There are certain probes. Okay. Each probe has a small complementary oligonucleotide. Does it make sense? And this small complementary oligonucleotide may have a fluorophore, fluorescent tag. As soon as you take this total RNA and put into this high throughput read, each oil has a different sequence, correct? once a complementary sequence is there, it hybridizes. Complementary oligonucleotide coming from here. Does it make sense? So now it lights up. Does it make sense? So basically what that analysis is telling, in this particular RNA pool, you have certain RNA which is expressed. Does it make sense? You can quantify how much. Now if you compare the control versus prostate cancer, you can actually figure out what are the genes they are going up, what are the genes are going down. Now, not only it analyzes the messenger RNA, but you have tons of other RNA which are expressed in that particular cell. Does it make sense? So now, along with ESA, we have many other potential candidates which can tell more closely the status of the disease. Does it make sense? So there are many RNA which are in clinical trial. One of them is called PCAT1, PCAT18, prostate cancer specific RNA, long non-coding RNA. They are actually, along with this ESA, just strong biomarker. Field is less than 10 years old, 2007, correct? At least several non-coding RNA are in clinical trial very fast, and they are starting. So it is, the field is rapidly evolving for discovery of variety of biomarker, especially function, but still it is at infant stage. We don't understand what these RNAs are doing in the cell, but we know they're expressed or down the way. Does it make sense? They're strong biomarkers. So what we want to do, they are also transcribed. The same way the protein coding genes are transcribed, they are also transcribed. We are not getting into detail of this, but we will understand what is the basic mechanism of transcription. So you have a double helical DNA, double-stranded DNA. One of the strands acts as a template. One of the strands acts as a template for making the complementary mRNA, complementary RNA. Whether it's mRNA, tRNA, ribosomal RNA, or non-coding RNA, all of them has to be transcribed. All of them has to be copied. Does it make sense? They have to be transcribed. So when there is a transcription going on, you have a double-stranded DNA. One strand is complementary to the, basically these two strands melt like DNA replication. And one of the strands acts as a template to copy the complementary messenger RNA or RNA. Does it make sense? This particular DNA template, which acts as template for RNA synthesis or transcription, correct, is called the template strand. You want to get some of these things very clear in your brain. Unlike DNA replication, where both strands are copied, in transcription you have two strands, only one strand is being copied into complementary RNA. Does it make sense? So this RNA, what is the relation between this RNA sequence which complements the template strand? What is the relation between sequence of this RNA and non-template strand? They are identical sequence, correct? Except that RNA has uracil, correct? RNA has uracil group instead of thymine. Does it make sense? So basically in transcription, again, you need a template. Let's go to the basics. you have a double stranded template, correct? And this male, one of them acts as template, another is called non-template. Get them very clear. The template strand is copied into RNA. Okay. So again, the transcription chemistry is same. We have a template. Let's say a TGC this is RNA and has a 3' hydroxyl group. So let's say this is G, this is C. Is it clear? Yes.
Earlier we drew a picture of this with the promoter, the gene. We had 5' is upstream and 3' is downstream. But then over here, when it we had 3' upstream and 5'
I will come to that. So basically that's telling you about the gene orientation. I'll talk about it. So get this one. So this is your template. Here 3' end, you have hydroxyl group. It's like DNA replication. The incoming nucleotide incorporates at the 3' end. There is no distance. So you need a template. But unlike DNA polymerase, you don't need the primer to initiate the transcription. Okay? No primer is needed. You need DNTP, DATP, not DNTP, you need nucleotide triphosphate, ribonucleotide triphosphate, correct? In case of DNA, you have deoxy. Here you have normal ribose, correct? ATP, GTP, CTP, and UTP. Does it make sense? Of course, you need polymerase, you need RNA pol, and you need metal ion, magnesium, or other metal ion to activate. Does it make sense? Now the chemical reaction is identical or similar to DNA replication. We have correct? Which nucleotide will come now? A? Uracil, correct? So uracil will come. Now you have normal ribose, OP, correct? Everybody agrees with me? Uracil triphosphate activated by enzyme and metal ion. Enzyme is RNA pol, correct? And you synthesize G, C, U, A with 3' hydroxyl group free. Does it make sense? So your chemical reaction is same. But although I started with this RNA, actually the beginning part of the RNA, unlike DNA polymerase, you don't need a primer to start with. RNA polymerase can synthesize its own first dinucleotide. Does it make sense? The first dinucleotide synthesis can be made by RNA polymerase, whereas DNA polymerase cannot do it, so it needed a primase. Does it make sense? RNA-based primer. So once it is done, you go on. Unlike DNA polymerase, most RNA polymerase do not have the proofreading activity. Correct? No proofreading. So of course, in the incorporation of the nucleotide, there will be wrong nucleotide incorporated. So you will have a RNA which is with wrong nucleotide, mutated, correct? But we discussed that mutation in RNA is tolerable because if there is a wrong nucleotide incorporated, either RNA will be degraded or it will make a new correct, or the protein will be made which is with changes in amino acid. Does it make sense? And it may not function well, it can be degraded. Correct? Because RNA and proteins are short-lived, they are not hereditary material except some RNA viruses, correct? So evolution can tolerate the no proofreading activities in RNA polymerase. Does it make sense? So they are short-lived. So you don't need, there are a couple of differences between replication and transcription. You don't need a primer. The most RNA polymerase do not have this proofreading activity. You need UTP instead of thymine. Does it make sense? So RNA is meant to be degraded. Why? Designed to be degraded, shorter half-life. Why? Why do you think that RNA should be short half-life? Easy to regulate. Correct? Whenever you need, you turn on the RNA transcription. Whenever you don't need, turn off the transcription. At the same time, you degrade it easily. So easy to regulate. That's why the half-life was there. So this is the basics of transcription. So one of the, what happened? Did I turn it off? No. Okay. So you need a template. You need a non-template. The other strand is non-template. The non-template strand sequence is identical to the messenger RNA, which is produced because it is complementary to the template, except that it is U. Now, couple of other nomenclature. Once these mRNA is produced, mRNA, this is 5 prime, this is 3 prime. Okay, this mRNA acts as template for protein synthesis. So mRNA kind of actually the sense for the protein, correct? So that's why this is called the sense strand. mRNA sequence is the sense because mRNA sense, correct? That's a template for protein synthesis, and the template non-template strand will be equivalent to the sense sequence. The template will be complementary to the mRNA. Does it make sense? This is called anti-sense. Does it make sense? Try to get some of the naming because there is plus minus. But once you get clear in your mind, it does not matter what they say the template, non-template, sense, anti-sense, and so on. Does it make sense? So we introduced actually a couple of very, very important basic transcription biochemistry. We introduced the concept of template, non-template, sense, anti-sense, RNA structure, and in case of protein coding gene, we have a gene which is a coding sequence, we have regulatory sequence which is called promoter, which is normally the 5' end of the gene. So now some of you asked, I think, what is this? This actually is representing the mRNA sequence. Okay, we code in that direction. So this will be 5' end, this will be 3' end.
The mRNA wouldn't have a promoter, right?
mRNA does not have promoter. This sequence is represented considering that this is mRNA. Okay, so normally this is the 5' end, this is the 3' end, and towards the 5' end of the mRNA, you will have promoter. Look at there, right? Right here.
Oh, okay.
So this is your mRNA 5' end. So this side you have the promoter where transcription starts. Does it make sense? So the promoter is at the 5' end of the mRNA sequence. There is a lot more complicated regulation. We don't want to go here, but I want to get you the what is the significance of transcription, how the basic transcription is done, or how it is designed to be regulated. Does it make sense? So, sense, anti-sense. I think I want to stop here. Next class we start with RNA polymerase composition, the function of different transcription, initiation, elongation, and then we start with. Then we'll go a little bit on regulation. Okay?